Hi guys, so today we're going to look some more at parametric equations. So what we're going to do today is we're going to look at a specific style of question, some projectile motion. So think of something, an object having a certain velocity being shot at a certain angle. So these are some things you may have seen in physics, and we're going to use parametric equations in order to model these. So we're going to use the calculator as one option here, and then there's going to be a second video that's going to show kind of how to find these points a little bit more algebraically. Now it'll still involve the calculator, but it'll give us a little bit more of an exact answer. So for today, we're kind of going to look at how to estimate it and get a pretty reasonable answer using our calculator, but it's not going to be the best and most exact. So if you want to find that or spend a little bit more time in it, then check out the other video that's going to go into a little bit more detail. All right, so the first thing that we're going to do, I went ahead and reset my calculator so you guys can kind of see this from the beginning. So the first thing we want to do is change the type, so F3, to parametric. And that's going to give us that X1, Y1 option. So that equation that you guys have listed over there, let's talk about what these things are. So V is going to stand for our initial velocity. Theta is going to be the angle that the object is launched at. H is going to be the initial height. T is going to be our time. And since we're using parametric equations, when we plug these in, we're actually going to use T in our equation. That's kind of like our X because we're having X equals and a Y equals. So if you notice, there's three equations up here. This first one is going to represent all of our horizontal distances. The other two, you're going to use one or the other, and it's going to represent the vertical distance. The one that you'll use is dependent on if you're going to use meters or feet. So if our problem is in meters, we're going to use this one because the gravity is negative 4.9 is the value that we would use because it's that 1/2 AT squared. Same thing if we're using feet, we're going to use this negative 16 T squared because we're using that negative 1/2 AT squared value for feet. So X is going to represent our horizontal distance, and Y is going to represent the vertical distance. All right, so let's go ahead and start by actually writing one of these equations. So first thing we have is Judah is going to launch a rocket off level ground with an initial velocity of 63 feet per second and an angle of 84 degrees. So we're going to write a set of parametric equations. That means there's an X equals equation and a Y equals equation. So the formula for X equals, it's velocity, which is 63, times T, which is our variable, and then just like it's always been, X is cosine, and our angle here is 84. Then for Y equals, we're going to do negative 16 T squared, plus velocity times T, since it's vertical, it's sine, 84. And then the initial height here, it says it's launched off the ground, so we don't need to add anything additional at this point. All right, so I'm going to go ahead and type these equations into my calculator. I'm going to lose them over here because I can't type while this is put up, so make sure you have those written down, and we'll go ahead and plug those into our calculator. All right, so once those equations are in, we're going to need to change our mode and make sure our mode is in degrees. Now, normally the way we do that is we do shift setup, but if I go from this screen, if I go to shift menu, and I scroll down, I don't think I'm going to see angle as an option here. So, actually I do have it, I apologize. It's just a little bit further down. So we'll go ahead and make that degrees now. Now, if you couldn't find it, you would go back to run matrix, but it actually is in here. So shift menu and then change that to degrees because we are talking about the cosine and sine of 84 degrees. All right, so now if I go ahead and graph this, we're not really going to see much of a graph. So what we're going to need to do is we're going to need to adjust some things on our window. So I'm going to go ahead and go to my window. So I'm going to do Shift F3. And let's talk about our X min and our X max. That's going to represent our horizontal distance that we're going to travel. Now I'm going to start at 0 because we don't care about negative distance. Our X max we can kind of guess, okay, and just see how it looks and adjust it if we need to. I'm going to make it 50 for now and just see what happens. Our Y min is our height, so again, I'll start at 0, and I'll just kind of guess here, and I'll go to 50. Now, these are things we can adjust once we see our picture drawn. And then, did not mean to press enter, I apologize. Let's scroll down here to these T values, and let's talk about what these T values mean. All right? Our T min and our T max is the number of seconds that this graph is actually going to draw. All right, so we don't need 360 seconds. This rocket is not going to be off the ground that long. All right, typically, a lot of the problems that you're going to see in here are going to be like 5 seconds or less, maybe. So I'm going to go ahead and make my Tmax 5. That PTCH is going to be how often it's graphing a point. So right now, if I were to go ahead and graph this, let me just show you what it would look like. I don't see an entire graph, okay? That's because I don't have enough of those t values for it to actually graph. So I'm going to go back to my window and I'm going to change that. Now, I'm going to go ahead and make it 0.01, and this is what we'll use for a lot of our problems. That's going to give us enough detail without it taking too long to graph. So now I'm going to go ahead and graph this, and I can see a pretty good picture. So you'll notice I see enough of my x's. I can see this rocket hit the ground and leave. So let's go to change our height. Okay, I can't see the top of this curve, so I'm going to go ahead and change the height. So I'm going to go to my window. Height is the y's. I'm going to make that y max bigger. If I make it 75 now and I try and graph it, now I can see this entire graph. All right, now let me show you a couple other problems that could occur. Let's say I make that T min and T max, or let's say I make that T max too small. Let's say I make it 2. If you notice, my graph stops. So if you see something like this, now almost all the pictures we're going to see are going to be these nice, pretty little parabolas. If you see something like that stops, you're going to need to fix your T values. Okay, so in general, a good idea is to use a min of 0, a max of 5, and that PTCH of 0.01. All right, so now let's go back to our picture. So now we're going to try and answer our questions. So what I'm going to show you guys on here is how to estimate these values with a calculator. The other video is going to go into more detail about how to find these a little bit more exactly and a little bit more algebraically. But for now, we're just going to use the trace function here, or the gsolve values. One thing you'll notice is your typical values on gsolve, like root, it's not going to give us anything. Gsolve max, it's not going to give us anything, even though we actually do have a max here. Now, what we can still use, if you do F6 and you do ycal, that's the only feature we really can still use. But notice it doesn't have you plug in an x, it has you plug in a t value. So what I could do is answer this second question. After 3 seconds, how far has the rocket traveled vertically and horizontally? That means when t equals 3, what's x and what's y? So what I'm going to do is I'm going to go to my t and I'm going to plug in 3. So now what you'll notice is it gives us two things. It gives us an x and it gives us a y. So what this is telling me is that when t equals 3, after 3 seconds, my horizontal distance would be 19.76 feet. That's going to be the horizontal distance. Vertically, I'm going to look at what the y is, and the y is 43.96 feet. So that's how far it's traveled vertically and horizontally after 3 seconds. So now we want to know when the rocket will hit the ground. So again, here's the problem. I can't use my normal functions on gsolve. Gsolve root doesn't give me anything because it's not a y equals equation. So what I can do to estimate it is I can press F1 to trace. Once you do that, you can start clicking right and left and notice that that t value is changing. And you notice the more you press it, you can start to see it kind of pop up. There's that little pink thing that's moving. So just remember what these different things stand for. Okay, t is your time. So where I stopped it right now, that's where it is after 1 second. X is the horizontal distance and y is the vertical distance. What you also will notice is that it's increasing exactly by 0.01 seconds. That's because that PTCH value that we used, that's telling us how much this little t is going to move by. So I want to know when it's going to hit the ground. I want to know what t value will make this hit the ground. Well, right now I'm just kind of following this path. And if you keep looking at those y values are positive, which means it's still above the ground. Well, now I'm at 0.99, 0.37, now it's at negative. So like I said, this method we're just using to estimate it. We're getting pretty close, okay? Somewhere between 3.91 and 3.92 seconds, this rocket is going to hit the ground because the height goes from positive all of a sudden to negative. So again, if we want to find it more exactly, I'll show you guys how to do that in the other video. But if I want to find when it will hit the ground, that's going to happen at about 3.92 seconds. So this allows us to estimate about what these things are going to be. All right, now let's answer those other two questions. So how long does it take for it to get to its highest point? Well, we're going to do the same thing. We're going to trace. So F1 to trace, and then let's just scroll until we get to the highest point. And again, this allows us just to estimate, and it'll get pretty close. It won't be perfect, but it'll get us about where it is. So let's look at those Y values. These Y values are still getting bigger, which means we're not at the highest point yet. So let's keep scrolling until we get the highest possible value that we get. So they're still getting bigger. They're still getting bigger, 61.3. And at this point, right around here, okay, that height's not changing much, but you can start to see in that range, that's where our maximum value is. All right, so right about here, I've got 61.33 to 61.33779. So right about there at 1.96. That's about as close as we can estimate. That's going to be the highest point. So that tells us three things. The time that occurs, that's the t value. That is 1.96 seconds. Okay, so this is t. The horizontal distance, that's x. So that is 12.91 feet. And then down here, the maximum height, that is the y value. And that is 61.34 feet. Now again, these are estimates just based off of tracing, but it gets us pretty close. All right, now let's look at another situation here. So now Jordan is kicking a football off level ground with an initial velocity of 66 feet per second and an angle of 40 degrees. So we're going to start by writing our equations. It's x equals velocity times t times cosine of 40. Then we've got velocity times, negative 16t squared because we're in feet. Velocity times t times sine of 40. And he's kicking it off the ground, so there's no initial height here. So let's go ahead and plug these into our calculator. All right, so my equations are plugged in. If I keep the same window that I used last time, I can kind of start to see what I need, okay? So you can see how this graph is going, but I have enough height, I don't have enough distance. This graph stops. So let me go to my window, and I need more horizontal distance. So let's make this value larger. Okay, and again, you can kind of estimate here. Sorry guys, I don't know why my screen just blacked out. But let's make that value a little bit larger. So we can just kind of take a guess here. Let's just try 100 and see what it does. So let's graph it now. So pretty close. So now I can see the highest point. Looks like I still need some more horizontal distance. So let's go to my window. Let's make our x max bigger. This time I'll just go ahead and make it 200. And now I can see my nice pretty parabola here. All right, so the first question wants to know how long the ball was in the air. So that's going to be the time where this graph hits. We're looking for this point right there. Okay, we want to know what the t value is at that point. So again, to estimate that, we can just trace to get close. So let's trace my t-step, or on a ti, it's called a t-step. So if you're using a ti, that's what we're talking about. But the PTCH, it's at 0.01, which means this is giving me every 0.01 of a second. So it goes a little slower to scroll, but it is a little bit more accurate. So let's keep going until we start to get to those negative numbers. So we're getting close, it's still above the ground, and now we're below the ground. So somewhere there in between 2.65 and 2.66. So again, either of those is going to get you pretty close, but again, we're talking about the t value here. So I'm going to go ahead and just estimate it at 2.65. All right, now we want to know where does the ball land if it was kicked from the 25-yard line and aimed straight down the field? Well, we just found how far this is going to travel horizontally. Okay, it's in the air for 2.65 seconds, and it travels about approximately that 134 feet or so. So if it travels 134 feet and it starts at the 25-yard line, then that's going to tell us how far down the field that it would go, which would be at 159 feet away from, well, 134 feet from the 25-yard line, 159 feet if we look at just the total distance, which isn't really on your field. So you can look at it either way. But it goes 134 feet away from where you were standing. All right, now we want to find the maximum height of the ball. So again, just to estimate here, we're going to go ahead and trace. If you want to see those more exact ways to find it, we'll do that in the other video. All right, so I'm going to trace here. And again, I'm going to trace to that highest point. Because that PTCH is 0.01, it's going to get me pretty close here. So let's keep looking. So those values are getting bigger. All right, so right around here, we've got 28.12 is going to be that highest point. So we want to know the actual height. The height is the y coordinate here. So the highest y coordinate that I find here is 28.12 feet. So a lot of this is just interpreting of what these different things stand for. So just remember, t is going to be your time, x is going to be your horizontal distance, and y is going to be your height. Tracing and scrolling is going to get us pretty close. It's just not going to be the most accurate. And I'll show you guys the most accurate again in the other video. All right, let's try another one. Let's write the equations out. So a golf ball is hit with an initial velocity of 135 feet per second. So 135t cosine 22. Negative 16t squared, because we're talking about feet. 135, whoops, that's an extra one. 135t sine 22. And then again here it is off the ground. We don't need to include any sort of an additional height. So we want to know if the ball will clear a 25-foot sand trap whose nearest edge is 300 feet from the golfer. So here's our golfer. Okay, they hit that golf ball. There's a sand trap that's the nearest edge is 300 feet away. So there's our sand trap. The sand trap is 25 feet. So what we're saying is, will this ball travel 325 feet before it hits the ground? So we can find this a couple different ways. Again, we can figure out algebraically, or we can just kind of trace and kind of estimate. So I'm going to go ahead and trace here. All right, now if you guys are ever having trouble seeing your picture, make sure you do remember to put those t's on both equations. Sometimes they get left off, and that'll really make your graph have some trouble. All right, so let's graph this. All right, so I can see, again, I don't really have enough horizontal distance. I have enough height, but not enough horizontal distance. So let's go to our window. Let's make that x max bigger. I'll go ahead and make it like 400, and that should be enough to see it. And there's my golf ball. So again, we want to see, is this going to clear something that is 325 feet away? Well, let's trace and let's find out. All right, so again, we're just trying to see if it's going to clear that sand trap. So 300 feet away, you can already start to see your horizontal distance. We're getting pretty close to 300 feet total away. My calculator's freezing a little bit on me. Sorry, guys. All right, so let's go and see where we are at 325 feet. So again, check that horizontal distance. Currently, we're about 300 feet away, so now we're at the front of the sand trap. So let's see if it's going to clear the back of the sand trap. So there we go, 325 feet, and it is still 23 feet in the air. So yes, we are definitely going to clear that sand trap. If you want to keep going, you can see how far this golf ball actually will go, but it's going to go definitely far enough to clear that sand trap. All right, let's look at our last one. So Katniss shoots an arrow from a height of 5 feet with an initial velocity of 25 feet per second at an angle of 15 degrees. So we actually have a different height now. So our x equals equation is the same, 25t cosine 15. Y is going to equal negative 16t squared plus 25t sine 15. And then we do have an initial height of plus 5 that we need to include. So let's go ahead and graph this on our calculator and see what it looks like. All right. All right, so once I have my equations typed in, we'll go ahead and graph it. And you're based on what your window settings were in the last question, you're not going to be able to see a very good picture. So what we're going to do here is make our y max and our x max smaller so we can get a better picture. So I do not need that x max to be that big. I'm going to go ahead and make that shorter. We'll go ahead and stop it at 50. And that y max can be smaller as well. I'll go ahead and drop that down to 20. Again, these don't have to be the exact same numbers, but as long as you're making them smaller, you're going to start to see a better picture of this graph. All right, so our total travel time here, let's go ahead and trace and get a good estimate. So again, we're looking for as those y's become negative. So those y's are still positive, still positive, still positive, negative. So somewhere right in there between that 0.79 and 0.8 seconds. All right, again, we're not going to get too exact right here, but we're going to be pretty close. All right, and that's when it is going to hit the ground. All right, let's go ahead and try our next one, our maximum height. So again, I'm going to trace here. Looking for the biggest y value I have. So 5.64, 5.65, and then it starts getting smaller. So 5.65 is going to be my biggest height right here. So that maximum height is 5.65. When will the arrow be 10 feet horizontally from Katniss? So let's trace, and this time we're going to be checking an x value. Okay, let's keep tracing. We're going to see when our x is 10. So when x is 10, there we go, right in there between the 0.41 and 0.42. And again, since we're estimating, either one's going to be close enough. So we'll just say 0.41 seconds. So again, you're looking, what is t when x equals 10? That's what you were searching for there. Then the last one, a squirrel is standing 18 feet away and is 1 foot tall. Let's see if we are going to hit him. So let's keep scrolling. And let's see what happens as our x gets closer to 18. All right, so we're going to scroll. My calculator's going quite slow because my computer is running like crazy. Just so you guys know, if you are using the iPad, through VMware calculator, it's going to look like the one that I'm using on the screen here. All right, so here we go. So there is when x equals 18. So at 18, my height is below 1 foot. So yes, if it's 18 feet away, I am going to hit it. But I just noticed on my notes, I apologize guys, I changed that to 15. So let's see if he'll hit him at 15 feet. So if I go back to 15 feet, let's see what our height is. Well, at 15 feet, all right, so if that squirrel were 15 feet away, then we would not hit him because 15 feet away, I still have a height of about 2.75 feet. So 15 feet, we are not going to hit that squirrel. Another way you could look at this if you wanted to, let's say that squirrel was 15. If I wanted to, I could actually plot a dot to show me where that squirrel is. I'm going to go to my x2, 15 feet away and 1 foot high. And now when I draw my graph, you'll see there's a little dot there. There we go, my little red dot. So you can see that it is going over the red dot where the squirrel is. So that's another way that you could check just to see. So 15 feet away, it would hit it. Let's see if he's 18 feet away. Oh, wrong button, sorry about that, guys. If he were 18 feet like I originally wrote it, but changed it, then that red dot is actually right on the line. So that would hit just the top of his head. All right, so that is it. So again, this is the kind of rounded estimation way we can use the calculator by tracing. If you check out the other video, that's going to show you more algebraically how you can find these values a little bit more specifically.